Yeah, so in the previous 3 videos, we laid the groundwork for understanding how the transformer model in the Attention is All You Need paper works. So we started with a basic form of self-attention for introductory purposes, and then we discussed the scaled dot product attention found in the Attention is All You Need paper. And then we talked about multi-head attention, that is running multiple of these scaled dot product attentions in parallel. And these are all components of the transformer model of the original or vanilla transformer model, which is found in the Attention is All You Need paper. And in this video we will go over the architecture a little bit in more detail, how the architecture of the transformer looks like. But before we get to the transformer, let me just briefly recap the scaled dot product attention, because it's part of the transformer and so that we have it fresh in our memory. And the second reason is because I spent so much time making this slide, I would at least like to talk about it for a little bit, so it was not all for nothing. All right, so on the left hand side here, that is just the summary of the scaled dot product attention from the original Attention is All You Need paper. I structured it into 5 steps here so that we can talk about it step by step. So step 1 is constructing the queries, the keys and the values. So imagine you have an input X, which where the rows are the different words. So let's say the first row is word 1 and the second row is word 2. Of course, in a real data case you have many more words, but so that I can fit everything onto the slide, we keep the example here small. And then the columns is the embedding size here, the word embedding size. We multiply it by a matrix WQ, that is a matrix that is updated during backpropagation, and this produces the queries. So still the first row corresponds to word 1 and the second row corresponds to word 2. We repeat this whole process to get the keys and the values, and in the original paper the dimensionality here of these is all the same. The only difference also here between computing the queries, the keys and the values is that we are using different weight matrices. But we are using the same inputs, of course. All right, so we have now the queries, the keys and the values, and then in step 2 we do the matrix multiplication between the queries and the keys. So that is down here. So if we consider the first word, we multiply it, or we compute the dot product with the first word here, because the first column here is also the first word because we have the transpose. So this one would be then really the relationship between the first word with itself, and then for instance first row and the second column would be the relationship between the first word and the second word, and so forth. So we can really think of this as something that captures the relationships between the words, if you think of the dot product as a similarity or a compatibility measure here. Then in step 3 we are scaling. So we are scaling by square root of dk. So dk is the size of the keys here. That is to prevent the softmax from being too sharp, because if we have large dot products or very negative dot products, very positive or very negative ones, then we will be at the ends of the softmax having values close to 1 and close to 0, which does result in small gradients. It's not so good for training. Step 4, we then actually apply the softmax. So just calling softmax on that to normalize. And then in the last step, step 5, we multiply our relationships here with the values. So then what we will end up with is with the first here, it's like the relationships of the first word corresponding to the whole context. So it's still, the first row is still corresponding to the first word, but now it contains information of all the other words. This you can think of as a weighting. We are weighting it with the other words. For instance, if we consider this, let's make this cleaner here. So if we consider the first row, and this one, like I said, captures the relationship between word 1 and word 2. So this is word 1 and word 1 and word 1 and word 2. So it's all the relationships for word 1. And then here are the first elements of word 1 and 2. And this captures then word 1 essentially with the relationships with word 1 and 2, if that makes sense. And then we continue. So we do that for all the other positions here and end up with these here. So it's essentially incorporating information about the other word, about word 1, but also word 2. If we had a longer sentence, it would be a little bit more interesting, because then we would have a larger context here. But essentially, it's about incorporating the context for each word, the context of the sentence. So that's the idea between the scaled dot product attention. So then we had multi-head attention. So what is multi-head attention again? Multi-head attention is repeating this whole process in parallel. So this is again from the original paper. So we are now repeating this H times and then concatenate the results and then apply a fully connected layer. So here I try to visualize that by having 3 matrices instead of 1. So we get 3 queries and so forth. And that's of course also true for the keys and the values. And you can think of them as different slices or different layers, and you can compute all of these H ones in parallel. Then you concatenate them, so you get these A's. If I go back one slide, so you get H times this A, and then you concatenate those, and then you multiply it by a weight matrix, and this is the fully connected part here. So here it is. Here, that's the transformer architecture. And I know it looks pretty complicated at first glance. There are lots of little details, but we will be able to understand it by tackling it one thing at a time. So I made a couple of slides where I will explain all these little details going on here. So in this slide, let's start with the big picture. So we can see the big picture is that we have 2 parts, an encoder and a decoder here. And the encoder receives input words, so that could be a sentence. It will produce a representation of that is then passed to the decoder together with outputs, shifted outputs. I will get back to that later in a later slide. But the big goal here is that it will produce the output probabilities for the words to be generated. So it's generating a sentence, and you can think of it as, let's say, translating a sentence. It reads an input sentence, and then it translates the sentence by generating 1 word at a time. And there are some familiar parts to it. So first of all, notice we have the multi-head attention here. That is what we talked about in the previous slide so much. So that's the multi-head attention from the previous slide that we talked about. It also appears here and here. There's actually a masked version. We will talk about the masked version also in a separate slide. Other things you might notice here is also that we have skip connections. So these skip connections are essentially the residual connections that we talked about in the residual network in the CNN lectures. Similar concept where we add the input to the output of something that went through a layer, right? So what we are doing here is we are, let's say, taking this input here, and we are adding it at this stage after the multi-head attention layers. We're doing the same thing here. So here we are optionally skipping the feed forward network. So for instance, if this is not learning anything useful, then we will have just forwarded the input here. So this skip connection is essentially adding it. And this is also why here we have certain dimensions. So originally the input embedding here is the sentence length T times 512. So we have a input embedding size of 512 in the original paper. They defined it as 512. And what comes out of here, of the multi-head attention, is also a 512 dimensional embedding. That is so that we can then add those together. So that's why we have the same dimensions. Same is true for here and here. So the multi-layer perceptron layers here, the feed-forward or multi-layer perceptron layers, they are matrix essentially WO, which is 512 as the number of columns. So it's 512 times 512. What else? Yeah, I think this is maybe it for this slide. So like I said, I don't want to talk too much about every detail in one particular slide because then it gets too cramped. Maybe one more thing highlighting here, there are more residual connections also in the decoder. Speaking of which, so the encoder and decoder parts are also repeated. So you can maybe see here in a small font, there is this NX. So this just means that they are repeating the encoder blocks and decoder blocks a couple of times. So in fact, in the original paper, they repeat that 6 times. So we have 6 encoders and 6 decoders. The structure of the encoders and the decoders is the same, it's just repeated. There is no weight sharing. They are separate, so they are separate encoders, but they have exactly the same structure, and the same is true for the decoders. So next, let's talk about masked multi-head attention. So what's that now? Do we need another video about masked multi-head attention? Don't worry, it's essentially the same concept as the multi-head attention, except we are masking some inputs in the sequence. So essentially it's about masking subsequent sequence elements. So here the decoder is generating one word at a time. And let's say we are having a sentence consisting of 10 words. We are currently generating word 5. So we would be at this stage masking words 6, 7, 8, and 9, and 10 that are already present in the training data set. So if we have a training data set, we have access to the full sequence, but we are masking those words that are not generated yet, essentially. So this will allow the model to attend to positions up to and including the current position. And how this masking works is by setting values as input to the softmax to -infinity, so that when softmax processes them, there will be zero probabilities. So this might look a little bit obscure, so I made another slide illustrating this masking. 1 second. So let's consider we have the input sentence, I like plants, and we want to translate it into German. So the correct German translation would be Ich mag Pflanzen. And this is known during training. When we're training this transformer, we know the correct translation. But when we're training it, we are training the model to produce one word at a time. The input is provided as full. It will produce then a representation of that input. But then let's say we have already generated the word Ich, and we are currently about to predict the second word. This is what we want to predict next. We are giving the model the whole sequence here as input. But it would be kind of cheating if we would show the model these 2 words, because these have to be generated. We assume right now only the first word is generated. So it would be cheating by just giving access to these words to the model here at this stage. So we are masking them. So here, that's what I try to illustrate. We are masking these words so it doesn't have access to them yet. Once it has, let's say, generated these 2 words, we will unmask this word and only mask the last word that it has to generate, and so forth. One more detail here. So the output size, what we are predicting here, this is one computationally expensive step, because the outputs here are the predicted probabilities for each word in the dictionary. So if you have a dictionary, if you think back of the RNN, the examples of the RNN when we had the word RNN for classification, I think we had a dictionary size of 20,000. So we have 20,000 probabilities for each word, and then we pick the word with the highest probability and get the index for that, and then this is our predicted word at this given position. So it's here by the highest softmax probability in an autoregressive fashion, which means essentially one word at a time. And the output size here of this linear layer is the word dictionary size, like I mentioned, which goes to the softmax for normalization. And then we pick the largest one, and then the learning is via cross entropy here. All right, let's now talk about this positional encoding here. So there is something that is added to the input embeddings. So if we think about the scaled dot product, the self-attention, how it works is that we are essentially relating each word, the query, to all the other words in a sentence. That's the self-attention part, but there is no notion of where the word is located in that sentence. So it's kind of invariant towards where the word is in the sentence. We are relating it to all the other words, but it doesn't really matter if that's the first word of the sentence, the last word, and so forth. We could get the same values. It's kind of the same concept like with multi-layer perceptrons. It's not really aware of the position in the sentence, right? So if we would shuffle, like I talked about before in a previous lecture, if we would shuffle all the columns in the data set, we could technically still learn the same multi-layer perceptron. So here it's about making the model behave slightly differently if the word is in different positions of the sentence. So here they have this notion of the sinusoidal positional encoding, which is added as a vector of small values to the word embedding vector. So they're using a sine and cosine function here, and they are like, let's draw them like somehow like this. They are not totally overlapping. They are a little bit positions by one position to the right and so forth. And essentially it's about capturing these. So there will be essentially a vector depending on which position. So if we have different functions or values of sine and cosine, and then we have the different positions in the text, let's say 1, 2, 3, 4, 5, 6, and so forth, then we will be extracting this, which is a unique pattern for that position. So for instance, just for simplicity, we would have two values here, and these two values are different in position 1 compared to position 3, for example. And we are just using that as a simple way of providing some position information. This is just to kind of get different results depending on where in the sentence the word is located. And that is all there is to it, essentially. Just as a reminder, also the input size and the output size are the same. This is so that we can repeat this 6 times and then also have the skip connections. I should have added this information maybe earlier, but that's also fine here. Okay, so next let's talk about these add and norm layers. So what are those? We can find them here everywhere in the network. And the add corresponds to the residual, the skip connections that I just mentioned again on the previous slide. But what is now the norm part? So the norm corresponds to layer normalization. We haven't talked about that yet, so I wanted to actually talk about it in the convolutional neural network lectures, but they were already so long that I decided to skip that. But it is essentially related to batch normalization. Here's a visualization of the different common forms of normalization in convolutional networks. It's from a paper called Group Normalization. So we are focusing now on, let's say, batch normalization, and this is here shown in the context of convolutional networks, where, as you remember, we are normalizing across the batch dimension. So you can actually, so here they have that separate, the height and width and the color channels. So here, essentially, you can think of H and W as the features, and the for one channel, and then you have the different channels here, and then N is the batch size. And here the blue part is how or where we get how we normalize. Here we are normalizing across N, so we are getting the mean and the sigma for the normalization from the batch dimension. In layer normalization here, we are getting it across the layer or channel dimension. So in this case, when you think of the multi-head attention, we would do it across these attention heads essentially. So we have, like I mentioned before, multiple attention heads, right? I think it's 8 in the original paper. So we have 8 attention heads, so we would be normalizing across the attention heads, computing the mean and sigma, and then the whole process is essentially similar to batch normalization. Lastly, to finish things up, here's an example of how attention values look like from the original paper. So if you think of attention values as values between 0 and 1, the attention mask. So if you think back of the Q, K, T, and then normalized. So if you, and then through the, through the softmax. So if you think of these, we can look at the attention values for each word towards each other word, right? And this is what's shown here. So for instance, when you look at the word law, it's kind of strongly connected. So the saturation here of the colors is how strongly it is connected. So you can see it's mostly connected to these here. It's the strongest connections. Maybe this one has a slight connection also to things further away here, but very weak connection to the missing, to the middle parts here. So yeah, this is just a visualization. And here in this visualization, it's shown for attention head, let's see, 5 and head 6. And you can see that it's actually not redundant to have multiple attention heads. You can see this pattern here is very different, let's say, from this pattern. So the attention head is actually, well, having different attention heads is actually useful, so it's learning different things in these different attention heads. Okay, so this was probably a very long video now on how the transformer architecture looks like. In the next video, I will talk also about some other more modern transformer architectures on a big picture level. So there have been these, for instance, popular models like BERT, GPT, and BART. Of course, there are many, many, many more, but these are one of the popular ones, the most popular ones. I will briefly talk about those, and then we will end this lecture with an implementation in PyTorch.